Okay.
All right.
Yeah. Very powerful. Take it away.
Okay, that was hard to follow up, but we're the ocean monitoring project. So it's comprised of me and Divya and Roy, who are connected via Zoom. And this is actually a picture I took from the Sally ride at the beginning of the quarter, and it just reminds us how beautiful the ocean is and why it's important to protect it. So there's lots of current data sets measuring water quality, pressure, temperature, and salinity. But what we noticed is that there's actually a lack of data measuring CO2 surface levels. And there's this ocean atlas called SOCAT. And actually the amount of values from 2017 to now are decreasing. So these are just measuring the values. And lately, we've been collecting less data from the oceans. And in fact, this is a plot from all of the data from 2023. And there's lots of portions of the ocean which are missing any sort of data on CO2 surface levels. And this is primarily because of cost. These measurements are taken with research vessels, which have huge operating costs. And of course, it's important to measure the level of CO2 because it gives rise to sea level, marine disruption of marine ecosystems, and ocean acidification. So this is kind of the problem that we're addressing. And there's this cool value chain plot taken from the scientific report, which shows how measuring data leads to changes. And in the end, I think the ultimate goal will be changing policies through international organizations. And so this shows how data is then mapped and modeled, which then leads to scientific reports and assessments, which then leads to changes by international organizations.
Or there could be an alternative history where we're writing the obituary of our planet. It will still be important.
Yeah.
No policy change happen.
Yeah.
It will be in the obituary.
That's true. That's a sad case, but that's true.
It's a sad reality.
Yeah. So this is our problem statement: developing a low-cost, autonomous platform for measuring surface CO2 concentrations. So I just wanted to give a little technical detail on the actual sensor we're using. So this is a photoacoustic sensor, which is super cool. There's a small microphone inside the sensor, which is cheap and actually reaches the resolution limit of Brownian motion of air. And they're quite cheap as well. Basically, there's an IR light which excites the CO2, which is absorbed by this spectrum right here, which then leads to pressure waves, which is then measured by the microphone. So I just wanted to give a little overview of the sensor. So here are the yes, there's an IR light and then a microphone.
I see. The IR is the excitation.
Yeah, the excitation. Yeah. So you can that's around. It's actually a live LCD display, so if you blow in it, you can see the CO2 and
But it says 622. It's in the future.
Yeah. No, it's because of our breathing.
Oh, because we've been trapping.
You'll see the level is gonna increase. It takes like
Yeah. Started changing. Okay, you should
yeah,
continue.
but you can touch it around. So in essence, we have a CO2 temperature
24 now.
and the humidity sensor in there.
624 ppm.
Yeah, and we also have a clock inside, and the total cost ended up being around $90. And Argo floats, for instance, cost $20,000. So this is an order of magnitude less. But I mean, it's not totally there. And we actually have a second prototype as well. And this is a lot more simple, but it's just a Pelican case. And what's cool about these Pelican cases is that they're entirely waterproof and they have a purge valve. So they actually vent some air, but are still waterproof. So you can pass through.
Yeah, and I think these cases are super useful because they are tested for certain amounts.
And so this one, we actually integrated a solar panel so we can have some, because the previous one just had a battery. So this is regenerative energy. And now Roy can talk about some testing we did.
Hello, am I audible?
Yes, you're audible, Roy.
Yeah, so this is the first testing which we did with the prototype one. And the surprising kind of thing which you can see in the beginning, that when it was pretty close to the sensor, there was a pretty like high noise and there's a sharp rise in the CO2. So the sensor could actually catch it. But what we noticed that to kind of getting standardized, it took quite some time. So in this case, around I guess 2 hours it took, and that is the how it looks, the temperature, humidity, and CO2 over the time period. In the second prototype is the similar thing, but as it was locked inside, it took around 3 hours to stabilize, coming back to the standard CO2 level that you can see at the right, and on the left we can have the whole how the fluctuations, everything is there. So these are two versions which we have worked on as of now. And then next,
Yeah.
Kevin, you're recording it, right?
Yeah. Is there, sorry, Roy, is there a way to increase the volume for, yeah, is there like
No,
a,
you have to project your voice.
yeah,
Okay, keep going, keep going.
yeah,
Yeah, we can hear him.
okay. So should I move to the next slide, Roy?
yeah, thank you. So
Okay.
now we have quite a lot of things we could brainstorm, and we found that which needs to be addressed. So one of the major issue which we found is like the waterproofing part, because we need a system which is open to only gaseous transport. It should be selective to only CO2, but not anything else. So that is one kind of thing which we need to address. For that, we found that there are some membranes like PTFE and PDMS, which if coated with actase can actually help in that. But the issue is sometimes if even the water vapor goes inside the particular chamber and it condenses, later on it can affect the circuit. So which we can see in the arrow, red arrow, that although they had kind of a covering, still the water vapor could seep inside, and after it condensed, and it could affect the whole circuit. So that is one major issue which we thought we need to address. Second is the biofouling part. So like as we are kind of making it for the ocean, and there are lots of organisms out there, so how we can make sure that we can make this robust and can keep it on the ocean for a longer period of time. So maximum, I have whatever literature we have gone through, we found maximum they're saying that 2 to 3 months they're able to keep. And for in some particular cases where they are using wipers along with UV and UV photocatalytic some materials, then the particular time length is a little bit more. So for so far they're using manual wipers, and people have also tried to, so if they have an optical window, they have tried to coat it with some material and then turn it into kind of a conductive surface so that it can electrify and anything does not get stuck on it. People have also tried to use UV and other material like TiO2, which essentially produces the ROS and which inhibits any kind of biofilm formation. So these are different kind of strategies available, but we need to still figure out which is feasible for our case. And we also need to now integrate with GPS module and the transmission and a self-powered system, which we are trying to figure out. So next, Divyanshi will take over.
Yeah.
So as we can observe, we are already in a lot of and experimental phase. We also come across the SOFA platform, which is approximately 42 centimeter in diameter and 5.4 kg weight-wise. It is already equipped with a lot of motion sensors, which measure weight, frequency, direction, wind, and all. Additionally, it is also having sensors which will measure sea surface temperature, barometer, dissolved oxygen, pressure, and temperature as well. So what we plan to do is, it also comes with Bristol mount development kit. What we plan to do is we plan to integrate this kit with our CO2 sensor so that we can get the carbon dioxide surface measurement. Also, we have applied on Bristol Mouse Pioneer program as well, and we are optimistic about it.
I mean, I think my intuition is that you could just integrate this with the buoy itself, and you need to do surface measurement.
Right.
The bristle mouth interconnect is really useful when you want in-water sensors and when the sensor package is big.
Right.
But since the sensor package will be very small, there's plenty pins available.
Yeah, that's correct. And also the bristle mouth, I'm not sure if there's a picture here, but there's also a CO2 sensor for water
Dissolve.
concentration. Dissolve water. So that would be
Also,
interesting as well.
much easier in this context.
Yeah.
Yeah.
And I'm going tomorrow to go visit the company.
Yeah. They are coming also this week, right? Peter is-
Right. Yeah. I'll get back to you.
Check.
Yeah, yeah.
Yeah, by the way, if anybody wants to visit so far, they've been our collaborator for some time now. We have 2 grants with them that we've written. They are in San Francisco, right next to the big pier where you take the Alcatraz. It's a super cool office because it's the original IDEO office. IDEO used to be this design firm that was started by 2 Stanford faculty. And so the office is actually pretty cool.
Oh, cool.
The office is on water. So if you drill a hole where you sit, you are sitting on water. It's like all on platforms. It's a super cool building. Okay, let's keep going.
Yeah, and that's about it. Also, that's not showing now, but I put it in the water fountain, the Stanford fountain.
Ooh, where
So
did you find a pool?
This is actually the Stanford fountain
It's
next to the tower. On the way here, I just had to put it in the water to test.
Edition.
Yeah.
Fountain popping.
So
Which fountain?
in front of the tower.
It's very important to quote which fountain.
Yeah,
Different fountain have different bacterial and
Yeah.
biological activity.
that's true.
Awesome.
Yeah, that's all.
Okay. For maybe one last quick question. What is the ppm number now?
17,000.
No.
No, but it's true. It's really our breath.
What?
And in fact, when I had it next to my desk. Yeah.
So it's accumulating, the CO2 is accumulating in the source. Right?
So it does diffuse out as well.
Yeah, but I'm just surprised that that happened so quickly. Because I passed that 600. 670,000.
But what was insane is I had it on my desk, and as I was working, I was collecting feedback. My microenvironment is 2000 ppm. When I left it alone, came back 500 ppm. Just goes to show.
Yeah, human breath. So
Yeah.
that's what mosquitoes rely on, is your microenvironment. Okay, question, any question? Vanessa and then Danny.
Oh, sorry, wait, Debbie, I was.
Debbie, go ahead.
Oh,
I was just gonna wonder, for your prototype, did you do it transparent like the other one? And that's the one
Yeah, definitely. So I added an O-ring here, so it's kind of sealed together. But this PET G is still not waterproof, so we'll probably need to make some powder.
I think we mold these.
Yeah.
Super easy to mold from a buoy point of view.
I wanted to know if you do like a batch of something because it has a cumulative cost.
Yeah.
But if something like that happens where it's just, I don't know, what's the minimum diameter of that, so to get the atmosphere.
It's something we've considered. We thought passively just adding a waterproof yet air permeable membrane might work, but we did
I
consider
mean,
also.
what's to be there? If it's gonna be in the ocean, it's gonna be rolling on the surface. This is measuring atmospheric CO2 in the open ocean. So you need a diffusive membrane that's gonna handle water. But there is no it's equilibrating. Right now, it's accumulating because we're not giving it equilibration time. So when it's sitting there, it's diffusing in and out, and you're just measuring the equilibrium concentration. I mean, SOCAT measurements are so important because I've said this a couple of times in the class. Ocean has 40x times the total CO2 in our atmosphere. 40 times more total CO2. And there are parts of the oceans that don't absorb CO2 but actually emit CO2. So it's ocean in total is a negative flux for CO2. But the Arabian Sea, for example, for some reason people don't understand, emits CO2. So this goes both ways. That's why these measurements have to be spatiotemporal. That's why CO2, like when people keep talking about that the Hawaii CO2 monitoring program might shut down. I don't know if some of you have seen what's happening to all the NASA satellites on climate have been shut down. Roughly around 100 climate programs are being proposed to be, not proposed. Many of them have shut down or are being shut down if this budget passes. So we don't have a choice but to take this approach and a citizens type of an approach to make these kinds of measurements. None of these measurements will actually continue. So that curve is gonna have a dramatic cut if you account for what is happening with the NSF. Okay, let's switch. I know there was another question, but let's catch up in the, who's next?